Whether angular momentum comes in units is very difficult for me to answer. At first sight, it appears that it is absolutely impossible that angular momentum comes in units, because angular momentum depends upon the direction at which you project the picture. You are looking at an area change, and obviously this will be different depending on whether it looked at from an angle or straight on. If angular momentum came in units, and say you look at something and it shows 8 units, then if you look at it from a very slightly different angle, the number of units would be very slightly different, perhaps a tiny bit less than the 8. But 7 is not a little bit less than the 8. It is a definite amount less than the 8. So it cannot possibly come in units. However, this proof is evaded by the subtleties and peculiarities of the quantum mechanics, and if we measure the angular momentum about any axis, amazingly enough, it is always a number of units. It's not the kind of unit like an electric charge that you can count. The angular momentum does come in units in the mathematical sense, that the number we get in any measurement in the definite integer times a unit. But we cannot interpret this in the same way as with the units of electric charge, imaginable units that we can count, one, then another, then another. In the case angular momentum, we cannot imagine them as a separate units, but it comes out always as an integer, which is very peculiar. Wow. There are other conservation laws. They are not as interesting as those I have described, and do not deal exactly with the conservation of numbers. Suppose we had some kind of device with the particles moving with a certain definite symmetry, and suppose their movements were bilaterally symmetrical. Look at the figure, please. Yes. Then, following the laws of physics, with all the movements and collisions, you could expect, and rightly, that if you look at the same picture later on, it will still be bilaterally symmetrical, right? So there is a kind of the conservation of symmetry character. Yes. This should be in the table, but it is not like the number that you measure, and we will discuss it in much more detail in the next lecture. Right. The reason this is not very interesting in the classical physics is because the times when there are such a nicely symmetrical initial conditions are very rare. Alright, and it is therefore not very important of practical conservation law. But in the quantum mechanics, when we deal with a very simple system like atoms, their internal constitution often has a kind of a symmetry, like a bilateral symmetry, and then the symmetry character is maintained. This is therefore an important law for understanding quantum phenomena, right? One interesting question is whether there is a deeper basis for these conservation laws, or whether we have to take them as they are. I will discuss that question in the next lecture, but there is one point I should like to make now. In discussing these ideas on a popular level, there seems to be a lot of unrelated concepts, but with a more profound understanding of the various principles, there appear deep interconnections between the concepts, each one implying the other in some way, right? One example is the relation between the relativity and the necessity for local conservation. If I had stated this without a demonstration, it might appear to be some kind of the miracle that if you cannot tell how fast you are moving, this implies that if something is conserved, it must be done not by jumping from one place to another. At this point, I'd like to indicate how the conservation of angular momentum, the conservation of the momentum, and a few other things are to some extent related. Right. Then the conservation of angular momentum has to do with the area swept by particles moving. If you have a lot of particles, look at the figure, next figure. Yes. And take your center X very far away, then the distance are almost the same for every object. In this case, the only thing that counts in the area sweeping or in the conservation of angular momentum is the component of the motion, which in figure 21 is vertical. What we discovered then is that the total of masses, each multiplied by its velocity vertically, must be a constant, because the angular momentum is a constant about any point, and if the chosen point is far enough away, only the masses and velocities are relevant. In this way, the conservation of angular momentum implies the conservation of momentum. This in turn implies something else, the conservation of another item which is so closely connected that I did not bother to put it in the table. Right. This is a principle about the center of gravity. Look at the next figure. Right. A mass in a box cannot just disappear from one position and move over to another position all by itself. That is nothing to do with the conservation of mass. You still have the mass and just moved from the one place to another. Charge could do this, but not a mass, right? Let me explain why. The laws of physics are not affected by motion, so we can suppose that this box is drifting slowly upwards. Now we take the angular momentum from a point not far away, x. As the box is drifting upwards, if the mass is lying quiet in the box at position 1, it will be producing an area at a given rate. Right. After the mass has moved over to the position 2, the area will be increasing at a greater rate, because although the altitude will be the same because the box is still drifting upwards, the distance from x to the mass has increased. By the conservation of angular momentum, you cannot change the rate at which the area is changing, and therefore you simply cannot move one mass from one place to another unless you push on something else to balance up the angular momentum. That is a reason why rockets in empty space cannot go, but they do go if you figure it out with a lot of masses. Then if you move one forward, you must move other back, so that the total motion back and forward of the all masses is nothing. This is how the rocket works. At first it is standing still, say, in empty space, and then it shoots some gets out of the back and the rockets go forward. The point is that of all the stuff in the world, the center of the mass, the average of all the mass, is still right where it was before. Wow! The interesting plot has moved on, and an uninteresting plot that we do not care about we do not care about has moved back. There is no theorem that says that interesting things in the world are conserved. Only the total of everything. Yes, only the total of everything. Discovering the laws of physics is like trying to put together the pieces of jigsaw puzzle, right? We have all these different pieces, and today they are proliferating rapidly. Many of them are lying about and cannot be fitted with other ones. How do we know that they belong together? How do we know that they are really all part of one as yet incomplete picture? We are not sure, and it worries us to some extent, but we get encouragement from the common characteristic of the several pieces. They all show blue sky, or the physical laws obey the same conservation principle. Right. Thank you.